All right, let's go ahead and get started. I want to welcome you to the second installment of part one. We're talking about matter. We've looked at the mixtures, and now what we want to do is we want to turn our attention to pure substances. Pure substances cannot be separated by ordinary physical means, like we saw in our last unit or our last installment of Unit 1. They include elements and compounds. So elements and compounds are pure substances. So for example, you can't take an element or a compound like water, for example. You couldn't take a water, which is a compound, and separate it in a distillation apparatus into hydrogen and oxygen. You would require some type of an electrical or excuse me, a chemical separation in order to do that. So all the elements on the periodic table are pure substances. So if you look up on the wall, there's a periodic table. All of those are pure substances. Hydrogen is a pure substance, so is oxygen, boron, aluminum, and we can go on down the list. But combinations of atoms are called compounds. Now, compounds are also pure substances. Compounds are also pure substances. So water, we've talked about already, H2O is a pure substance, but so are things like sodium hydroxide. I'm going to write the symbols for these. You won't know what they are just yet, but I'll put them down nonetheless. So sodium hydroxide, that is a compound, a pure substance. Calcium chloride. Don't worry about these formulas just yet, but I just want to have them written down so you can know that those are compounds. Ammonium hydroxide, silver oxide, etc. There are over 20 million compounds that we know of. All of them are pure substances. So although compounds can't be broken down by physical means, such as filtration, distillation, or evaporation, they can be separated by special chemical means. And that's what we want to talk about now, those chemical means. So what is a chemical process that can break down compounds such as water into elements which compose them? So let's talk a little bit about the apparatus. Well, the process is known as electrolysis. So remember, if I have water, that's a compound, and water cannot be broken down into its component elements through a physical process like, for example, distillation. But what I can do is I can use a process that's known as electrolysis. And this is a process by which water, which is a compound, can be separated into its component elements, hydrogen and oxygen, right? An electrolysis apparatus is shown below. Now I'm going to write the reaction. You're not going to understand entirely what the reaction is telling you, but I just want to write it down for you so you have some idea. So H2O then is the pure substance. It is a liquid, obviously, but it's also a compound. And so the idea is that I want to break down, that's what that arrow means. That arrow means a chemical reaction. Hydrogen into these two elements, or water into these two elements, hydrogen and oxygen. So that's the reaction that we're looking for, turning a pure substance, water, this compound, into its component elements. In order to do that, I'm going to need this setup. It's called electrolysis. The way that it works is I have two tubes just like this, and I have electrodes. One's called a cathode, the other one's called an anode. And I fill both of these with water. I'm going to have a battery set up so an electrical current is going to run from across the two tubes. And then what's going to happen is that the water, via the electricity that's running through the water, is going to be turned into oxygen, that's oxygen on the left, and hydrogen on the right. So balloons are placed above to collect the oxygen and the hydrogen gas, right? So what I've done is I've used this process that's known as electrolysis to separate oxygen away from hydrogen. So this is a chemical separation as opposed to a physical separation. I'm taking a pure substance, in this case it's a mixture, excuse me, a pure substance, in this case it's water, and I'm separating it into its component elements, hydrogen and oxygen. All right? So now we've looked at a physical separation technique, that's distillation, and we've looked at a chemical separation, that's electrolysis. Let's talk a little bit about the physical and chemical properties of nature. Physical properties are properties which relate to the physical nature of matter. They include such things as color, melting point, electrical conductivity, hardness, length, malleability, and density. Boiling point and texture are also physical properties. All right, so boiling point and texture are also physical properties. Chemical properties are properties which relate to the chemical reactivity of nature. So they include things such as the ability to rust and flammability. So for example, if I put a metal in the presence of water and oxygen, it's going to form a new chemical, rust. Flammability, something catching on fire, that's a chemical reaction. So if I said, for example, that acetone is flammable, we would say that that's a chemical property of acetone. Lithium reacts violently with water so that it's a chemical property of lithium. So that's a chemical property of lithium. So let's make sure then that we know the difference between physical properties then and chemical properties. Now let's talk a little bit about physical versus chemical changes. Physical versus chemical changes. Well, matter often changes in some way. We can describe these changes as either physical or chemical changes. So let's talk a little bit about physical changes first. Physical changes are changes in which no new substances are formed. If a dissolved material such as salt solidifies and becomes a salt crystal, that's a physical change. It was a salt before and it's a salt after. If salt deposits form or from evaporated seawater, that's a physical change. If ethanol is purified through a separation process known as distillation, that's a physical change since no new substances are formed. All phase changes are physical changes. Okay, so if you go from solid to liquid, liquid to solid, liquid to gas, gas to liquid, or a process known as sublimation in which we go directly from a solid to a gas, that is called sublimation, and that is a physical change. So that includes melting and boiling. When a salt dissolves in water, that's a physical change since you still got salt and water. There's no chemical processes that occur. When wax melts, that's a physical change. If a piece of glass gets broken, that's the small pieces, they're still glass. So that would be a physical change, right? There's no chemical process that is occurring, so that's a physical change. Gasoline or acetone vaporizing, that's a physical change as well. So is sanding wood. It's still wood, it's just in smaller pieces. Subliming dry ice, in other words, going from solid to gas, that's a physical change. The following diagram is a separating funnel. So this is a separation funnel. I'll show you one in the classroom. A heterogeneous mixture separates according to density. And the higher the density of the liquid, the separating from the lower density liquid. So I want to use this to separate a high density liquid from a low density liquid. So down here, for example, is my high density liquid, and up above is my low density liquid. The high density liquid will always sink to the bottom. The low density liquid will always float to the top. So is this a physical or a chemical separation, right? Is this a physical or chemical separation? Well, it's physical, since no new substances are formed and you end up with the same two liquids. They're just separated. So for example, if I had water and olive oil, the water would be on the bottom, the olive oil would be on the top. They're separated, right? Because of density differences and also because of differences in the types of forces that are holding them together, but nonetheless they're separated. So if I want to know what type of separation this would be, the separating funnel or separation funnel is going to be a physical type of separation. A physical type of separation. Now let's talk about chemical changes. These occur when substances are formed, when new substances are formed, the key being here, new. These are often irreversible processes and involve a change in color, production of gases, and maybe production of an odor. Examples might include an apple rotting, milk souring, or a hamburger being digested. So all those are examples of chemical changes. Now the hamburger is being chemically changed in your stomach or your tummy, right? Because the hydrochloric acid is digesting and forming new chemicals from that hamburger. Other chemical changes include a copper pot that tarnishes. Notice the color change, or a bracelet that turns your wrist green. A leaf changing color in the fall of the year is a chemical change. Notice the changing in colors is a sign that a chemical change is occurring. Burning or combustion of paper or wood is a chemical change. Now let's do a practice problem. All right, let's practice. So here we go. The question is, which of the following represents a physical change to a piece of granite? A physical change to a piece of granite. A, sulfuric acid from pollution weathers the granite. Well, anytime you're talking about a chemical, that's probably not going to be a physical change, okay? So sulfuric acid weathering the granite, the sulfuric acid is probably undergoing some type of a chemical reaction. That would not be a physical change, so we'll mark that one out. Iron fragments in the granite combine with oxygen in the moist atmosphere to form hematite or rust. Well, here we have a new substance forming, so that's a chemical change, right? So that's not going to be the answer either. Acid rain causing damage to the granite. Well, the fact that you have an acid, that's a chemical, right? That's a chemical. So when you're taking a chemical and you're changing granite, that's going to be a chemical change as well. Let's hope the last one is the correct answer. It says rainwater falls into an opening into the granite and then freezes, causing the granite to break into pieces. Okay, well, there's no chemical change here. In other words, the water is simply freezing, expanding, and then causing the granite to break apart into little pieces. That's it. That's our answer. So D would be our answer. That's the physical change that we're looking for. Okay, so that would be a physical change. Make sense? All right. Describing properties of nature. We're on page 6 now. Matter can be described in a number of ways. One way is through its properties. We can describe properties based on whether the property being described depends on the amount or not, right? Depends on the amount or not. Extensive properties depend on the amount of the material present. Extensive properties depend on the amount present. For example, mass depends on the amount. The more you have, the more it weighs, the more the mass is. Weight and volume, those are all extensive properties. They depend on how much you've got. Let's say you had a sample of iron. Its mass, weight, and volume would depend on how much you had, and so these are extensive properties, right? Those would be extensive properties. Well, let's contrast that now with intensive properties. Intensive properties do not depend on the amount of the material present. Examples include color. Doesn't matter if you have sulfur, it's yellow. It doesn't matter how much sulfur you have. Hardness, density, those are all intensive properties. The color and hardness of the iron sample that we spoke of before don't depend upon how much you've got, so these are intensive properties. They're intensive properties. Interestingly, density is also an intensive property. Now remember, mass and volume were both extensive. They depended on how much, but density, interestingly, is intensive. Why? Because density is mass divided by volume. The density of the iron is the same regardless of how big or how small the sample is. So you can have a small ingot or a giant piece of iron, the density would remain the same. Therefore, density is an intensive property. Now notice that boiling point and melting points are intensive property. It doesn't matter how much I've got. If I've got a little bit of water or a lot of water, it doesn't matter. The boiling point and the melting point remain the same. Okay, remain the same. All right. I think we'll leave these definitions for the next one. So I'll see you on the next one. Thanks. Bye-bye.